Hi, this is Nasnyanevsky. We're going through monoidal category theory. We're up to chapter 4, section 7, the Yoneda Lemma. So this is a famous, probably the most important theorem or lemma of category theory. And it's a very powerful statement that's used in many, many different places, okay, within category theory. And you just say, oh, it's the Yoneda Lemma, and whether or not it's true or not, everyone will say, okay, I believe you, whatever. Basically, what it says is, and we'll get to this towards the end, basically it says is that the properties of an object depend on the way other things are mapped into it, or depend on the morphisms. So that's the central idea of all of category theory, namely, the morphisms are the important things. But the point is that all the properties that you can find about an object really depend on the morphisms. So that's what it's about. Okay, there's a legend that there was a student, Nabua Yoneda, who went to a conference in Paris, and he met Saunders Mac-Lane at some train station, and he showed this to Saunders Mac-Lane. Saunders Mac-Lane published it, or whatever, said it with him, and that goes back to the 1950s, and since then it's been used. Okay, so this chapter is basically split into two parts. There's two parts. One is called the embedding theorem, and basically, let's just give you an outline. It says that for any locally small category, there's a nice embedding from there into the category like that. Okay? So what that says is this category, or some version of this category, sits nicely in this category. And the other thing is called, so that's called the embedding theorem, and the other thing is within this category, okay, the objects in this category are pretty much determined by the things that are embedded into here. So we will see that very nicely. Okay, so that's the foreshadowing that we will need. Okay, great. So let's look at this category very, very carefully. You have set to the A op. Op is some category. Okay. The objects of this category are basically functors from A op. So we'll call them, well, they're contravariant functors from A, or they're covariant functors from A op to set. Okay. And these have a fancy name called presheafs. Okay, and later on we'll see why they're called presheafs. But basically what they do is they assign to every object here a set here, and for every edge here a set morphism in the other direction. Okay, the morphisms between these things, there are many such presheaves, and the morphisms are basically natural transformations between them. Okay, great. So that takes care of that. Great. So that's what this category is, and we're going to spend this entire section in that category. Okay, and the main thing is this embedding theorem. So the embedding theorem is written like this. You have Y for the Yoneda, A is for the category you're talking about, and there is a functor from A2 set to the A op. The main point is, and again, I didn't prove that there was a functor yet. We will prove it. I didn't do it. But the main point is this is an embedding, which means injective on objects, full and faithful. Okay, so that's basically the statement of the Yoneda Lemma. Okay, but now let's go through a lot of those details and see what it is. First of all, how is this defined? And the answer is as follows. The embedding on a little object A is equal to homomorphisms in the category of A, contravariant functors from there to there. Okay, and basically, just to remind you, this is a functor. We've seen this before. This is a contravariant functor. It goes from A up, so it's covariant in this, whatever, to set. Okay, you give me a object in here, and I will give you a set, namely the Ham set, and you give me a morphism in here, and I will give you that. Okay, so that's the way it's defined. Such functors, such presheaves, really, that's a presheaf, but such presheaves are called, ready? Representable functors. Okay. Okay, now I just want to finish this off. Little a, and then you can plug in a b into that because that's a functor. That's basically equal to Ham of a on b comma a. That's the Ham set. Great, hold on. That explains how the embedding is, so basically, the category A sits in here as representable functors. And these are the core, I would say the word skeletal, but it means something else here. These are the core of this category. And that's the whole purpose of the Yoneda Lemma, is that this is the core. These representable functors are the core. Okay? The reason why it's called representable, in some sense, A, which is an object in here, is represented by this functor. Okay, great. But we're not only is it A, that's the way it's defined for object A, but how is it defined for morphism? So let's pick a typical morphism from A to A prime in A. Then we're going to have Y of A for F is going to be a natural transformation. Okay, and it's going to go from Ham of A to Ham of A prime. Okay, very important. Y of A, this is covariant. So now, sorry, we're going to see this over and over. F goes from A to A prime. This is covariant. So it's Ham of A prime. Very nice. However, each one of these is contravariant. So it's a covariant natural transformation between two contravariant functors. Got to keep that in your head. Okay, great. Now, okay, so this is the way it's defined. That's a natural transformation. This is the way it's defined for an arbitrary f. But let's just see what this is. This is the natural transformation. So it's going to depend on an object b. So that is the component of the natural transformation. And that's going to go from Ham of b comma a to one map, because this is a set, locally small, to Ham of b comma a prime. Let me show you how this is defined. Okay, so if you have a little map from b to a, which we can call h, then if we can compose this with f, we get from b to h, we'll call that a, and we'll have a to a prime, that's f, so that's a prime. Okay, so that's b to a prime. So that's the way this map is defined. Let's just say it post-composes with f. Very nice. We're going to see that later on, much later on today. Okay, great. Okay, now, that's the way this natural transformation is defined for morphisms. Okay, so let's just not forget where we're up to here. We have an embedding of A into set to the A up. Okay, so if you give me a morphism in here, we're going to get a morphism in here, natural transformation, and here's we're showing how it's defined on a particular element in A. Very nice. But the morphisms in here are natural transformations, not just like that. So we have to show a naturality condition. So let's do that naturality condition. And it goes as follows. Okay, so ham of b, shoot. It's going to leave out the little a. So b comma a. Okay, and this is y of a at f. I'm sorry, let's say this. That's a functor. That's going to be a natural transformation. That's going to be the component of the natural transformation. Ham of b of a prime. Okay, now, given, what did I call it? G, I need space here. Given G from B prime to B. Okay, so I want to show this is natural. So what I'm going to do is I'm also going to look at ham of B prime, comma A. Okay, ham of B prime, comma A prime. Okay, and this is also y of a, the Yoneda embedding under f at not b, but b prime. Okay, so here's two components, and the main idea is that we want these components to respect this morphism. So let's do this. Notice this goes from b prime to b, and we're going to have like this. Okay, so what's this? This is ham of g, comma a. B to b prime is contravariant in A, okay? And this is going to be ham of g, comma a prime. Okay, now, hopefully, this diagram will commute. That's what we're hoping for. Okay, so let's see if it works. I'm going to pick a typical, you know what? I'm going to use a different color pen because getting a little bit confused here. This is going to be, but this is what we have to do. And again, all the proofs in Yoneda Lemma are of the same form. So we're going to do it once very, very carefully, and we'll do it. You ready? Okay, so given a morphism from B to H, I'm sorry, from B to A in here, okay, this goes to, what does this do? Well, we're going to have B to A, H, and now we're composing it with this, G. So this becomes B prime to B, we call that G. So here we are precomposing with G. Very nice. Now we do this. What does this do? Well, it's going to do something very similar, B prime to B, take that to G, okay, take that to A, but now it uses this F. What's F? F goes from A to A prime. So this goes like this, A prime. Okay, so this is a G. So we take this H, we pre-compose it with G, we post-compose it with F. Very nice. But we need this to be natural. So let's do it here. Basically, you're going to have B to A, we'll call that H, and then you're going to first poke, this is using F, so we do that. We post-compose with F, and then follow it down like that, and pre-compose it with G, and we get the same thing. Okay, so let's just see what this says. This says, take a map, pre-compose it, and then post-compose it is the same thing as taking a map and post-composing it and then pre-composing it. Okay, this is all associativity of function composition. Nothing more than that. Okay, so you both get to the same thing, and conclusion, this diagram is natural. Very nice. Okay, let's go further. So, let's go through this again. You ready? So this is this y of a what did we show? We showed how it's defined on objects. We showed how it's defined on morphisms. We showed on morphisms that the thing is natural. Very nice. Okay, that still doesn't show that y of a is a functor. Okay, what do we need for it to be a functor? And the answer is as follows. If f goes from a to a prime, and f prime goes from a prime to a double prime, then y of a of f compose f prime is equal to y of a of f prime compose y of a of f. We want the embedding to preserve the composition of morphisms in A. Okay, and also y of a on identity of a should equal to identity of Hom dash a. Okay, I left this in the book as an exercise. It's not hard. It's just, it's not hard, it's just painful. Okay, great. So we have that embedding. Hold on, I didn't say anything about embedding. We have the functor, it's a functor, and we know how it's defined on objects. We assume this is correct. Now we assume this is correct. Okay, and what are we left with? Okay, very nice. Okay, before we go further, I just want to go through what I do it's a very nice example of two categories. Okay, and again, I'm trying to motivate the Yoneda Lemma, and so I talk about two different categories. One is called 3, and one is called 3 prime. They're very, very similar. Okay, this one has 3 objects, A, B, and C, and I'm sorry, I got to get the name straight. This is F, G, and H. Okay, and this one has 3 objects, A, B, and C, and it says 3 morphisms, F, G, and H. Okay, the difference between this category and this category is here we assume that F compose G is equal to H. Okay, and here we do not make that assumption. Here we do not assume that F compose G is equal to H. We assume it's not equal. Okay, to make that distinction, we do that. Okay, now I just have to say F compose G is equal to something, but not H. So there's another morphism there or something like that. Very nice. But I want to show you where this shows up in terms of representable functors. Okay, and the idea is as follows. If you look at Hom of 3, so that's 3, of A comma C maps from A to C, so it says that this is F composed H, F composed H. Okay, by the way, another name for F composed H is G. That's very nice. I'm sorry, I made a mistake here. No, this is wrong. It's right in the book, it's wrong here. This is, nope. Okay, as opposed to that, so this is what it's equal to this one element set, as opposed to this, Hom of A comma C at 3 prime, this other category, very similar, just this commutes, this doesn't commute, is equal to, you ready? F composed G, F composed H. That's one thing it's composed. F, it consists of F composed H, but also another thing, comma, separate, another thing is G. Okay? Main point. This category is very similar to this category, but there's one difference, and that difference shows up in the representable functors. And that's the main point of the Yoneda lemma, namely the representable functors have all the information of all the categories. So that's very nice. Okay, great. Okay, by the way, I'm still not finished. So that's just a nice example, and we're going to use this example also, but I'm still not finished in showing that this is an embedding, because part of this being embedding is that this is injective on objects full and faithful. Okay, now the way I like to think of this is a category. This is a way, way, way larger category. So the fact that this is injective on objects, that makes sense. Every single object here goes to a different representation theory, representable functor. Okay, but it needs a proof, and in the book I do the proof. Another thing is, the fact that this is faithful, what that means is two different morphisms here are going to go to two different morphisms here. That also kind of makes sense because this is very, very large. This is things where things don't get crunched down. But the important part of this is full. That's the important part. The important part of this embedding theorem, or the non-obvious part of this embedding theorem, is that it's full. Namely, any morphism from here to here, any morphism in here, full means any morphism between two representable functors comes from here. That's what it says. Now that's a little bit shocking because this is such a large thing, you would think that there's more morphisms. No, they're not. This is full. So let's go through that. That's the most important part of this. And it's as follows. Given a typical morphism between two representables, so given beta, which is a typical morphism between Hom dash A and Hom dash A prime, that's a typical morphism in here between two representable functors. Guess what? We're going to say that this natural transformation comes from a morphism in here. Which kind of says that the morphisms in here are very similar to the morphisms in there. Okay, now I need to do something here because I want to okay, so let's do it. Ready? Okay, so very nice. Given such a thing, I'd like to show it. First, let's explore a little about B, because B is a natural transformation, okay? And let's see what it is, okay? So let's go through this. Hom dash comma A, I'm not going to put the dash, hold on. Comma A, okay? Hom comma A prime, okay? So this is beta. Hold on, but we want to do it at a particular component, so we're going to do it at B. So here we have B, and here we have B. Very nice. Guess what? Oops, sorry. We're going to do it at another component. We're going to do it at another component, A. And A, and this is A. Hold on. We want to show this beta has naturality. So what do? We look at Hom of B comma A, beta of B, Hom of B comma A prime. Okay, again, we're given beta and it's a natural transformation, which means it's going to have to commute, which means as follows: for every k from B to A, this is going to commute. Well, hold on, we didn't finish it. Okay, so this is Hom of K comma A, and this is Hom of K comma A prime. Okay, great. So that's what it means for a beta to be natural. Great. Okay, I want to show you that this beta is actually from this functor. And so here's what I'm going to do. I'm going to start off with an element in here, but a particular element in here. There might be a lot of elements, but I'm going to look at one easy element. You ready? And this is always there. Identity of A. Okay, great. Now this is going to pre-compose, post-compose, I don't care, because we compose anything with A, what do you get? You get this K. So here we're going to get B to A. We're going to call it K. Very nice. Okay, great. Now you're telling me, here's the crux of this fullness proof, you ready? You're telling me that this is a natural transformation. So you know what? I'd like to know, what does this go to? And the answer is, it goes to some morphism from A to A prime. The identity is going to go to some morphism from A to A prime. What morphism should it be? You know what? I'm going to call that morphism from A to A prime, I'm going to call it F. Okay, great. That's very nice. Okay. Okay, now what does this go to? This is composing with, this composes with K, so what do we get? We get A to A prime, K goes from B to A, so here's F, and here's that. Okay, great. Now, this is natural. Okay, so what does this go to? Well, it post-composes with F. B to A, then you post-compose it with F. So what does this mean? What does this mean that B is defined by post-composing with F? We've seen functors that talk about post-composing. Basically, you ready? Y sub A of F post-composes with F, and that's exactly what B does. So Y compose is exactly what B does. I'm sorry, beta. That's exactly what beta does. Post-composes with F. Conclusion, you started off with something here between two representable functors. Guess what? It came from here. It's basically post-composing with F. Now, question, where the hell did this F come from? Or how did you find this F? Well, you found it right over here. If you post-compose with F and you start with the identity, you're going to get here F. So that's exactly what you have. Okay, main point. Every natural transformation between two representable functors comes from this. Okay, so we are now finished with the embedding functor. We are now finished with the embedding theory. Let's say it. We saw how it's defined on objects. We saw how it's defined by morphisms. We saw that when on morphisms, it gives you natural transformations. We saw that we didn't see, but we said that it's injective on objects and it's faithful, but most importantly, it's full. That's the core of the theorem. Okay, great. Now, I just want to point out something. I said it before, but we have to say it again. You ready? This functor is covariant. Okay, I made it as an embedding, so I did that, but it's covariant. However, each of its images are contravariant functors. So it's covariant between contravariant functors. Okay, very nice. Now, just in passing, because we'll see this we're not going to see it in our book, but if you study category theory, you'll see it. There's another Yoneda embedding theorem. There are two Yoneda embedding theorems, okay? And the other one is left as an exercise, but it basically says as follows. Take the category A, op. Okay, well, you can embed A op into set to the A. And we call this Y superscript A. So this is a contravariant Yoneda embedding theorem. And what it says is, this sits nicely in this. Okay, and let's go through this. And basically, I'm just going to show you how it's defined on objects. Y of A on little a is exactly what you think it is. Ham of A comma blank. Representable functors, that's a functor from here to here. Covariant functor from here to here. Okay, representable covariant functors. Okay, and the idea is it's full, faithful, injective on objects, just like before. A has to be locally small. It includes into that very nicely. Okay, let's go through that part again. It's contravariant. However, the image of each one of them is covariant. So that's the exact opposite of that. Okay, very nice. Okay, so now what I want to do is I want to look at this. Let's forget about the contravariant functor. So let's go back to our classic set to the A op. Okay, so I want to look at this category very carefully, and I want to say inside this category there's ham dash A. I'm sorry, I want to deal now with the category 3. Okay, so let's deal with the category 3. So that's a very nice category 3. If you want, you can deal with the category 3 prime. Okay, and this is 3. Very nice. Oh, that looks like a B. 3. Let's just write 3. Let's leave out the boldface. 3. Okay, so we can talk about that's a representable functor. That's a representable functor. That's a representable functor. Okay, all contravariant. Okay, I'm not sure. Okay, we have natural transformations like this and like this and like this. Okay, great, very nice. But you know, there are other functors in here. So here's another typical functor in here. We'll say F. F goes from 3 opposite to set. We'll call that F. Okay, very nice. But we could talk about functors from here to natural transformations from here to here, and here to here, and here to here. It's all within this category. Very nice. Okay. And now I want to state, I'm not going to prove the Yoneda lemma, but it's because it's just a lot of what we saw before, very tedious little exact things, but I'm going to state the theorem very carefully. Ready? And it says as follows. Ham of, say, I'm talking about in this category, of, okay, ham of A of dash comma A. So here's a typical representable functor in this category. I'm sorry, now we go back to A. So, sorry, we looked at the nice things beforehand, a nice example, and I motivated it, but we'll come back to the motivation, but let's go back to this. So now we're here. So this is a typical element in here. This is a typical element in here. Okay? Question, I'm interested in how the morphism, how many morphisms, or what are the morphisms from here to here? In other words, think of this. What are the morphisms from here to here? And the answer is, you ready? Boom, boom, boom. f of a. That's a set. It's a Ham set, so it's a set. Well, f of a is also a set. Okay? That's the Yoneda lemma. That's a statement of the Yoneda lemma. Okay? And then, of course, it's natural. This is natural, so everything works, and these commute, etc., etc. The main point is as follows. What did we say? That this is full, and if there's any other object in here, okay, or not if there's any, with any other object, the maps between them, the representable functors have all the information you need. And so the maps between them go like that. Okay? So the maps from here to here are represented by what's in here, by f. So main point, the information that f gives you is gotten from the representable functors. Okay, so let me try to motivate why it's important. And the idea goes back to chapter 1 when we talked about sets. So when we talked about sets, we said, you know what? Look at all the morphisms from here, the functions from here to here. Well, that tells you all about S in the category of sets. Okay, you could also look at 3-element, or sorry. You could look at maps, all the maps from here to here. You could also look in the one-object graph and look at that. Look at the maps from here to there in a one-object graph. And that tells you a lot. That tells you what the objects in the graph are. You can look at the graph homomorphism from here to G. That tells you what the edges of the graph are. Okay? Let's do some other examples. You have K, a field. You have K vector spaces. Well, that's also a vector space, a K vector space. And if you look at all the maps from here to here, those gives you the rays. Okay, those gives you a lot of the vectors in that. Let me show you something else. Take a topological space. What do topologists do? They look at the unit interval from 0 to 1 and they map it to T. They look at paths of T. Okay, in all these things, we're doing the same thing. We look at simple objects, and we look how they map into bigger sets, bigger graphs, bigger vector spaces, bigger topological spaces, and we say, oh wow, we're learning a lot of different properties about these things. We're learning a lot of different properties about these sets, graphs, vector spaces, and topological spaces. Same thing here. Okay, what we're doing is we're looking at arbitrary presheaf. Okay, and then we take these simple things called representable functors, and we look how these map into this, and that tells us information about this f. It tells you what it's equal to. So that's kind of the metaphysics of the Yoneda lemma. Okay, I just wrote it in English. The properties of an object are determined by the maps mapping into the object. Okay, and that's kind of like the centerpiece of all of category theory, that you figure out the invariant properties of objects by looking at the maps surrounding that object. Okay, one other way of looking at the Yoneda lemma goes as follows. Category of set is co-complete, which means it has all co-limits. Okay, any diagram, you know how to take a diagram of co-limits. Co-products is just disjoint union. Co-equalizers are just those things that you can set in equalizers and stuff like that. You can set things equal to each other, etc., etc. Very nice. So set is co-complete. Okay. Next, look at all the functors from here to here. Well, basically, co-limits in this category are figured out point-wise. In other words, you look at the way they are, you take a co-limit of these things, look what you get in terms of the sets, and this category is also co-complete. Give me any diagram in here, as long as I have a diagram this gives me a diagram in sets, and I can take the colimit that way. It's called pointwise. Okay, very nice. And the idea is as follows. Take a category A, and let's say I want to do co-complete the category. What does that mean? I want to make sure that this category has all colimits. Okay, so basically what you want to do is you want to think of A as a nice category, but it doesn't necessarily have all colimits. Well, I want to add in more structure to get all colimits. Well, there's a lot of ways of doing it. The smallest possible way of doing this, the shortest possible way of doing this, is to embed A into set to the AOP. This might not have all colimits. This definitely has all colimits, and it's the best, satisfies universal properties of having all the colimits. Okay, 1 second. Question, what happens if A is co-complete when you start? Well, in that case, this is an equivalence of categories. Okay, so that's the Yoneda lemma. So the Yoneda lemma is a nice way of showing, that the objects of a category are determined, the properties of an object of a category are determined by the morphism surrounding it. And that's the central point of all of category theory. Let's foreshadow a little. We have one more section in chapter 4. Namely, we're going to talk about categorical logic, which is logic that's done from the category point of view. Lots and lots of adjoint functors here. Okay, and we're going to talk about ands and ors and arrows and double arrows and knots, and we're going to talk about quantifiers and propositional logic and predicate logic. So it's going to be very nice. Okay, and that will be the end of the first part of the book. Okay, the book has basically 3 parts. The first part is an introduction to category theory, and most people stop after this in a typical undergraduate class in category theory. But there's so much more. There's so much more. We're going to cover next chapter 5, 6, and 7. We're going to cover monoidal categories, and we're going to boost up and get more structure in our categories and talk about a lot of things like that. And then 8, 9, and 10, we go on for more advanced topics and things like that. So the next section 4.8 is a mini course on categorical logic. Have a wonderful day.